Question 5, I decided I was going to take next. So that's the worryingly named physics compilation. So part A, the acceleration due to gravity on the surface of Mars is 3.71 meters per second squared. Mars has a radius of 3395 kilometers. Period of revolution 24.62 hours. Show that a satellite needs to be positioned 2.04 times 10 to the 7 meters from the centre of Mars so that it remains stationary with respect to an observer on that planet. So basically, geostationary orbit. Around Mars. So it's got to be at the equator as a geostationary orbit. But the point is, geostationary, that my satellite's up there. As the satellite rotates, does its orbit, the planet rotates at the same rotational velocity, so that our observer always, at the equator, always sees it overhead or in a constant position. Right, so we've done this one earlier, basically looking at the period of a satellite. So let's say the period, so for a satellite, centripetal force equals gravitational force. By that I'm saying the force on the satellite, the centripetal force that keeps it moving around that circle. Where does that force come from? It comes from the force of gravity. So it's not, centripetal force is never another force, it's always got a physical origin. In this case it's gravitational force. So we know that mv squared over r, where r is that distance, the radius of the satellite orbit, equals gmm over r squared, which equals, so what do we know, what do we want to find out? Obviously big G, do we know? We don't, we're not given big G. Well, we've got it in another question, so I don't think there's any reason why we can't bring it in from another question. But we are actually told what the acceleration due to gravity is on the surface. So we should be able to, and we're told the radius, so we should be able to work out some of these constants. So we've got that, let's do it that way, work out G times M from this information here. So we know at surface, the acceleration due to gravity must be gm, we lose that m, divided by r squared, where this is the radius of Mars. Let's turn that into capital R. So that implies that gm equals A at surface, which we know, times the radius of Mars, which we know. So therefore, we know gm, therefore, we know that there. Our m's cancel there. So we have v squared over r equals gm, which is a surface times capital R squared over r squared. So cancel one of those r's. So that tells us, what does that tell us? So we've got a relationship between our velocity and our radius. We want to know, or we know the period. The period's got to be 24.62 hours. So we know that the period is going to be our distance over velocity, which equals 2 pi. The distance is, that distance has 2 pi small r over our velocity, which is going to be the square root of a surface capital R squared over small r. So that's 2 pi is our r to the power 3 over 2 again, divided by square root of a surface square root of capital R squared. It's just r equals t proportion to r to the 3 over 2. That's Kepler's third law. So we know our period, we know the acceleration at the surface, we know the radius, therefore we can find our r. So r to the 3 over 2 is going to be t times the square root of a surface times capital R over 2 pi. So small r is all that to the power of 2/3. So t is, we're going to put all this into hours and things, so it's 24.62 times 3600 seconds, because we go to SI units, times square root of 3.71 times our radius 3395 times 10 to the 3 meters, divided by 2 pi, all raised to the power 2 over 3, and that's our distance r, and that's what's needed. So hopefully that comes out as 2.04 times 10 to the 7 square and bolt calculation.
It looks roughly like that.
It looks roughly the right kind of order of magnitude, yeah. I really should find my calculator at this point. We'll cut back to that one. Let's go on to, actually I'll go and find my calculator.
Okay.
I can always get it really, I'm sure I put it here. Okay, I can't see it. Okay, the moral of the story is make sure you turn out to the calculator. Right, going on to Puppy then, unless you've got any comments on that?
No, that's good. Well, actually, there's probably a couple of important points. One is that using the capital R and the small r,
Yeah.
those are one of those things which you can start mixing up, and using subscripts is not quite as effective in this case, I think, as using.
Yeah.
And the other one I think was, which most Year 13 students might struggle with, is equating the acceleration to gm over r squared. That's when you're just learning the material, you probably don't deal with that. So that's quite a one of the key points I'd suggest.
Yeah, the orbit thing is that, yeah, where's that centripetal force coming from? It's coming from gravity. Anything in circular motion, the force on its centripetal force is mv squared over r. It doesn't matter what's causing the circular motion, that is the centripetal force, the size of it. Must be g mm over r, and r squared in this case.